Welcome back to the podcast. Today we're diving into the fascinating world of distributed systems, focusing on quorums, fault tolerance, and the challenges that arise when nodes in a system fail or behave unexpectedly. Whether you're a tech enthusiast or a seasoned developer, grasping these concepts is crucial for building reliable systems. So, let's get started. At the core of distributed systems is the concept of a quorum. A majority quorum allows a system to keep functioning even when some nodes fail. For example, in a 3-node system, losing one node is manageable, while in a 5-node setup, 2 failures can still be tolerated. The important thing to remember is that there can only be one majority at any given time, which helps prevent conflicting decisions from being made simultaneously. Now, let's talk about the importance of uniqueness in these systems. There are many scenarios where it's crucial for a single entity to hold a specific role. For instance, only one node should lead a database partition to avoid split-brain scenarios. Similarly, only one transaction or client should hold a lock on a resource to prevent data corruption, and usernames must be unique to distinctly identify users. However, just because a node is designated as the chosen one, it doesn't mean it has the consensus of the other nodes. If a node was previously the leader but has been declared dead due to network issues or other interruptions, it may no longer hold the authority it thinks it does. This brings us to the risks associated with false beliefs. When a node operates under the mistaken impression that it is still the leader, it can lead to significant problems. A common example is data corruption bugs, where a client believes it holds a valid lease on a resource even after it has expired. This can occur if the client is paused for too long, giving another client the opportunity to obtain the lease and write to the resource. When the first client resumes, it might also write to the resource, resulting in data corruption. To mitigate these issues, we can implement a technique known as fencing. This involves assigning a fencing token each time a lock or lease is granted. When a client sends a write request, it must include its current fencing token. If a client with an outdated token tries to write, the system will reject that request, ensuring that only the most recent and valid operations are executed. It's also important to note that the resource itself must actively check these tokens. Relying solely on clients to manage their lock status can lead to inconsistencies. This proactive approach helps protect the system from clients that may inadvertently act on outdated information. Now let's shift gears and discuss a more complex scenario: Byzantine faults. These occur when nodes behave unpredictably or maliciously, sending false or corrupted messages. This issue is famously illustrated by the Byzantine generals' problem, where generals must agree on a battle plan despite unreliable communication and potential traitors among them. In distributed systems, Byzantine faults can arise in critical environments like aerospace, where data corruption can have catastrophic consequences. Here, systems must be designed to tolerate such faults, ensuring that consensus can still be reached even when some nodes are compromised. While Byzantine fault tolerance is crucial in high-stakes environments, it's often impractical for general server-side applications due to the complexity and cost involved. Most systems operate under the assumption that nodes will behave honestly, which simplifies design and implementation. However, it's wise to incorporate mechanisms that guard against less severe forms of lying, such as hardware issues or software bugs. For example, using checksums can help catch corrupted network packets, and input validation can prevent malicious attacks on publicly accessible applications. In practice, many systems utilize redundancy to improve reliability. Take the Network Time Protocol, or NTP, for instance. NTP clients can contact multiple servers to synchronize time, ensuring that as long as a majority of servers are functioning correctly, the system can ignore any outliers. As we wrap up today's discussion, It's clear that understanding quorums and fault tolerance is essential for anyone involved in distributed systems. By implementing strategies like fencing tokens and being aware of Byzantine faults, we can build more resilient systems that withstand failures and maintain integrity. Thanks for tuning in. We hope you found this episode insightful. Don't forget to join us next time as we explore consensus algorithms in greater detail. Until then, keep questioning and learning.